All right, so here is our exam review part two. This is the one you're going to want to do because this is the one that's going to be worth points. Seventh period got kind of a bad deal because the internet didn't work seventh period. So that first review, if you did it, outstanding, is going to help you. But if you didn't, don't worry about it because this is the one that's going to be worth points. So remember, if you're doing with a partner, feel free to put names on it, but beware because we got Sally and Fred here. This is Sally and she's allowing to put Fred's name on it. Now remember, make sure Fred knows what he's doing. If Fred is not helping, if Fred's playing video games or watching videos, Sally, if I were you, I'd say Fred, sorry, not this time. Because if Sally rocks the test, Fred has no clue what he's doing. It's going to affect Sally's score on her exam. So, put a name there if you want, but make sure your partner actually is doing the work and knows what they're doing. All right, so I'm going to go over two of each of these problems. So it says combined gas law. So it's labeled. So obviously we're going to use this. But if you don't know, look, it's given us liters, which is volume. It's given us atmospheres, which is pressure. It says nothing about moles. So it's not asking for moles, which is N in the ideal gas law. So we don't need the ideal gas law. We're going to use the combined gas law. And what's it giving us? Once again, it's giving us volume, liters, and it's giving us pressure. Nothing about temperature. So we don't need the bottom. We just scratch it out. And here is our new equation to figure out this problem. P1 times V1, pressure 1 times volume 1, equals pressure 2 times volume 2. And that's just filling in some numbers. So our initial volume is 3.2 liters. 3.2 times our pressure one is 1.5. 1.5 atmospheres equals, what do we got? 0.8 atmospheres. That's P2. That's pressure. 0.8. And it wants us to solve for what's the new volume? V2. All right, so it's just solving. It's just simplifying. I'm going to start with the left side. I'm going to go 3.2 times 1.5. 3.2 times 1.5 equals, on the left side, I got 4.8 equals, over here, I got 0.8 V. To get V by itself, I got to divide both sides by 0.8. Divide this side by 0.8. So then all I got to do is it's going to give us V equals, so 4.8 divided by 0.8. 4.8 divided by zero point 0.8 equals 6. So the answer to this, the new volume will be 6 liters, L for liters. And voila, there's one combined gas law problem. On to the next. All right, so another combined gas law. Now let's see this one. This one's given us pressure in atmospheres, P1. It's given us volume in liters. Oh, and it's also given us temperature. So it's not asking for moles. Since it's not asking for moles, we're not doing the ideal gas law. We're still doing combined gas law because it's giving us pressure, volume, and temperature. And this time, since it's given us all three variables, we can't scratch out one. Like last one, we got to scratch out the temperature on the bottom. This time we got to use the whole thing, but it's not that hard. All right, so it's just filling in equations. Temperature is always on the bottom. Pressure and volume's always on the top, but you don't have to remember that because the equations will be provided for you. All right, so what's our first pressure? P1 is 1.25. So 1.25 is P1 times V1 is 4. I mean, it's 4.00, but 4 is the same as 4.00, so I'm going to save some space. And our T1 is 300 Kelvin. 300 Kelvin on the bottom equals, what do we got? So this is ATM is pressure. So our P2, the second pressure, because it's changed, is 0.950. I'll just put that. And it's not giving us the volume. So that's what we're going to solve for. And our T2, our temperature 2, is 360 Kelvin. All right, so what I like to do, I'm going to start by simplifying the left side. So I'm going to go 1.25 times 4. 1.25 times 4 equals 5. But then I got to divide it by 300. So 5 divided by 300 equals, so on the left side, I'm going to write over here, we got 0.017 equals. Now over here, I got 360 on the bottom. I gotta get V by itself. So since 360 is on the bottom, it's like dividing. I gotta do the opposite. I gotta multiply. So I'm gonna multiply both sides by 360. So 360 times 0.17 times 360 equals, I get 6. All right, so now I've done this. I multiplied 360 times this, and I'm going to get, so now I got 6 on the left side equals, since I multiplied both sides by 360, it's gone. Now I'm stuck with just this, equals 0.95 V, volume. And now to get V by itself, since this is multiplying 0.95 times V, I got to do the opposite. So I got to divide both sides by 0.95. So I got to do it to this side as well. I'll just put 0.95 because same deal. All right, so now the answer is just going to be 6 divided by 0.95. So 6 divided by 0.95 equals, and there we go. So it's going to be V2 equals 6.32 atmospheres. And there you have it. There's a combined gas law problem where all three variables are in there. All right, so let's try another one. All right, so now this one says ideal gas law. But remember, on the test, it's not going to have it labeled for you. What we look for, it's giving us volume liters, it's giving us temperature. Oh, it's giving us a constant. And it's also asking, or it's giving us moles as well. There's moles. Since it's talking about moles, now we're using the ideal gas law. Obviously, it was labeled as that, so it makes it easier. But it's asking for moles, which is N. N is moles. So now we got to use the ideal gas law. So I think these are actually easier, but anyways. All right, so PV equals nRT. Well, you need to memorize that. You will not. PV equals nRT. All right, so what do we got? So we got V, we got volume is 12, PV. So 12 is our volume. And we're solving, we want to solve for pressure. So it's not giving us pressure. So it's not giving us P. So PV, P is going to go on the left side. Doesn't matter if it's in the front of the 12 or the back, they're multiplying. So, it doesn't matter, if you get those flip-flops, it just got to be on the left side of the arrow. Equals nRT. PV equals nRT. N is number of moles. So here's our number of moles is 2.2. 2.2 moles. PV equals nRT. R is for the constant. It literally puts R right here. So here's our constant of 0.0821. PV equals nRT. T, of course, is temperature. It's always temperature. And where is it? Oh, here we go. 300 Kelvin. You see the K. Oh, it doesn't say temperature. We should know by now that K Kelvin is a unit of temperature, and it's 300. All right, now this time I actually got a little, oh, I lost my pen. It don't matter. All right, so let's bring out my old calculator app. So now I'm going to simplify the left side. So 2.2 times the constant 0.0821 times 300. So see, I haven't used this yet. So 2.2 looks pretty easy times 0.0821 times 300 equals. All right, so on the right side, we've got 54. Oh, no, it went away. Let's see what it was. 54.1 something. 186. 54.186. Don't really like that it goes away like that, but oh well. Equals, on the left side, we got 12P. So we got 12 times P. All right, so to get P by itself, we should know by now, this is 12 times P, so we got to do the opposite. We got to divide. So we got to divide both sides by 12. And let's bring the calculator out. So 12 divided by 12, of course, is 1. We're going to be left with 1P. So it's 54.18 divided by, that's 12. 12, not 0.2. All right, so we got 54.18 divided by 12. 54.18 divided by 12 equals 4.515. All right, so I got to remember that. 4.515. So P equals 4.515. And since it's P for pressure, it's going to be atmospheres. Voila. All right, there's an ideal gas law problem. Let's move on to the next area. All right, so now we're on to the ideal gas law. So we go up here. Remember, this will be provided for you. Now, whether it's the ideal gas law or calorimetry, you're going to use the same formula. It's right here. Q is energy that the system contains in joules. M is the mass. How much matter does that substance weigh? How much mass does it contain? C is the specific heat of that substance, and it's different for all substances. For water, C of water, specific heat of water is it takes 4.184 joules to raise 1 gram of water 1 degree Celsius. That's its specific heat. And delta T or triangle T means the change in temperature. All right, so let's go to our specific heat problem, and there it is right there. All right, so let's see what we can do. So Q equals MC delta T. Once again, you won't have to memorize that. So what is it giving us? It's giving us M. Let's see, what do we need to solve for? Okay, we're solving for Q. It's asking for how much energy. So we were solving for Q. So that's our variable we got to solve for. MC delta T. Here's our mass. It's in grams. Oh, I didn't know grams is mass. Well, you eventually need to know that. Mass is in grams. So our M, our mass is 55 grams. C, what's the specific heat? Here it is. Our C for what is it? Aluminum is 0.897. So our specific heat of aluminum is 0.897. All right, so we got MC. Now we need delta T. All right, so the initial temperature was 22. The final temperature is 72. We need to know how much that changed. So when it raised and when it went up from 22 to 72, that's going to be an increase in 50 degrees Celsius. So I'm going to put for our delta T, our change in temperature is 50. All right, so now we got all of our numbers. I'm going to dump that little app, my calculator app, because I don't like that it goes away. And now all we're doing is this times that times that. And if you don't know what the button is for multiplication on a calculator, it looks like that. All right, anyways, so 55x or times 0.897, the specific heat of aluminum, times 50, our delta T, our change in temperature, equals Q. This is how much energy is in the aluminum. How much energy in joules? 2,466.75. So I'll round it off to 0.8. And voila. There is the energy of aluminum when you got 55 grams of it and its temperature raised from 22 to 72 degrees Celsius. All right, on to the next one. All right, so now a calorimetry question. So we're going to be using the same formula. We're going to be using the same formula for specific heat. Q, energy in joules, equals mass times the C, specific heat, times the delta T, or the change in temperature. The only difference is we're going to have to do it twice because we're going to try to figure out what metal is heated here. The metal is heated. It's put in water. I mean, you measure the temperature of the water, how much it changed, and you can figure out what metal it is. So I'm not doing 16. So those of you guys that are just like copying down my answers, but you're not listening, I'm doing 17. So I know if you put the answer to 17 up here, like I'm going to, I know you're not even listening. I'm doing it up here because I need to make sure I have a lot of space. It's hard for me to draw on this thing. All right, so here we go. Q equals MC delta T. So first thing, we heated a metal. We don't know what it is. We put it in water. We know how much the metal, how hot it is. And we're going to measure to see how much energy the water gains. How much hotter, how much heat, how many degrees Celsius did the water increase by? All right, so MC delta T. Q, so we're figuring out Q. How much energy did the water gain? MC, so N stands for mass, and the mass of the water is 100 grams. So our M is 100. C, what's the specific heat of water? Right here, 4.184 joules. So C equals 4.184 joules. Delta T, delta, change in temperature. So the original temperature of the water was, the final temperature is 25. The original temperature was 22. So obviously, the temperature of the water went from 22 to 25. It increased by 3. So delta T, the change in temperature is 3. All right, so now this is going to tell us how much heat energy the water gained from the hot metal. And it's just multiplying them. So 100 times 4.184 is going to be 418.4 times 3. So 418.4 times 3 equals the water gained from the hot metal. It gained 1,255 0.2, but we'll just round it off, joules. All right, that's how much energy the water gained from the hot metal. Now, the water didn't make this energy. Conservation of energy cannot be created or destroyed. It can just be transferred. So this is the energy that got transferred from the metal. So that's the amount of energy the metal had, the hot metal. So now we're going to try to figure out, we're going to solve for the specific heat of the metal. So we're going to solve for C in our equation. So Q equals mc delta T. We got Q. This is the amount of energy that the hot metal had because that's the same amount of energy that the water gained. So our Q, we know now, it's 1,255 joules equals M. We got to know the mass of the metal. How much is it? Where is it? 46.6 grams. 46.6 grams. That's our mass. Specific heat, we don't know. That's what we're trying to solve. Someone put a C for specific heat. Now I need to know, what did the metal, what did it change by? Metal at 95 degrees. So it started at 95 degrees. And when it was done, it ended at the same temperature as the water at 25 degrees. So 95 and 25, the metal went down by 70 degrees. The change in temperature, delta T, is 70. Doesn't matter. I just need to know the change. So it could have been negative 70, but I always make it a positive number. So it changed by 70 degrees. So now all we're doing is solving for C. So here on the right side, I'm going to go 46.6 times 70. 46.6 times 70 equals 3,262. So on the right side now we have 3,262 C equals, and on the left we still have the same thing, 1,255. All right, so now to get C by itself, we're going to divide both sides by 3,262. 1,255 divided by 3,262. And when we get that, when I do that, C is going to equal what? All right, so 1,255 divided by 3,262 equals, I get 0.385. 0.385. All right, so that's what I calculated as the specific heat of the metal that was placed in the water. So now we go over here. And here we go, right here. 0.385 matches up perfectly to the specific heat that we calculated. So the mystery metal that was put into the cooler water, the hot metal put in the cooler water, is copper. All right, there's a calorimetry problem. All right, here are a couple. I'm going to do some of these. I'm going to describe some of these enthalpy problems. I put my calculator away because in this class, we're not going to do any calculations when it comes to enthalpy. If you're in honors, you would, but not in this one. All right, so I'm not going to label this diagram because it's too hard. I'm going to tell you the answers, but I'm not going to write them. All right, so these are energy diagrams. This is a chemical reaction. The entire thing is what's called the system. The system is like the beaker or the test tube that the chemical reaction is occurring in. It's the actual chemical reaction itself. That's the system. Now, everything surrounding it, the air or the container, that's called the surroundings. So either energy during the chemical reaction is being released into the surroundings. So if something gets hot or like a firework blows up, that would be exothermic because it's releasing energy into the surroundings, into the air, into the container, whatever. Now, if energy is absorbed, the system absorbs energy from its surroundings, then it's going to be endothermic. All right, so you will need to know, you're not going to need to do any math in the enthalpy in our class, but you're going to have to recognize an energy diagram and kind of describe it. So you need this one you're going to be labeling. I'm not going to write this. You're going to have to be listening. Sorry. All right, so reactants, where is it? Here's our chemical reaction. This is the system. Here are our reactants right here. There are the reactants. There are what's going into the chemical reaction. They're going in. This is what comes out. So you can see the energy of the reactants is the potential energy is way up here. So the higher up it is, the more potential energy it has. The lower it is, the less potential energy that substance, those chemicals contain. All right, here's the activation energy. This is the energy required to get the chemical reaction started. It's kind of like lighting a fuse. You light a fuse on a firework. That's going to allow the firework to, take off in the air or whatever. But first, you got to light the fuse. You need some activation energy to get the chemical reaction started. All right, so once it goes down, that's when the chemical reaction starts the beginning. But here, there's no change. Right here, we started with this amount of energy with the reactants, and when it reaches here, we still have the same amount of energy, but it doesn't stop there. You can see it continues going down. So this right here, this is going to be our delta H. This is our enthalpy, our energy change is right here. So we went from here to down here. And this is where you're going to want to label products. So this is what gets made. So like Nike makes shoes. So the products of Nike are shoes. This chemical reaction made this, whatever this is. And this you can see how it's lower. This is lower than this. So the energy of the products is lower than the energy of the reactants. Therefore, the system lost energy. The chemical reaction lost energy in the form of heat to the surroundings. Remember, the surrounding is just everything that's surrounding the chemical reaction. So if the reaction is in a test tube, the test tube itself or the air around the test tube, that would be the surroundings. And in this case, the surroundings is going to heat up because energy started here in the system and it went down here. So energy got released. Since energy got released, I'll label this, but I'm not going to do the whole thing. Since energy was released from the system into the surroundings, this would be an exothermic reaction, EX. I'm going to put EX for exothermic. Now, is delta H change in energy change, is it positive or negative? And we don't care about the surroundings here. We care about the system, the chemical reaction right here. It's in this graph. So since the energy started up here, high, and the products, low, energy from the system was lost, which made it exothermic. Since there's now less energy, the products have less energy, delta H is going to be negative because we lost energy. We didn't gain. Whenever you lose, that's negative. And now we'll look at this one over here. On this one, here are our reactants right here. There's what's going into the chemical reaction. You can see the potential energy of the reactants is very low. Here's our activation energy. You're gonna have to label this. I'm just drawing arrows. Activation energy to get the chemical reaction started. Here's the actual chemical reaction right here, and it stops right there. Here is our products. So you can see the energy, the potential energy of our reactants, very low. The energy of the products is higher. Where did that energy come from? The chemical reaction doesn't make it. Conservation of energy. It can't be produced and it can't be destroyed. It can just be transferred. So this increase in energy came from the surroundings. So the system, this chemical reaction, absorbed energy from the system and it put it inside the products. Since energy was taken in, was absorbed from the surroundings, this would be an endothermic reaction. I'm going to put En for endothermic. Is delta H positive or negative? Change in heat, change in enthalpy. Is it positive or negative? Since the system gained energy from the surroundings, it is going to be positive. Will you need to know this? You will. All right, I'll do the next ones here in a second. All right, I'm not going to do these because there's only two. There was only two here as well, but this should be easy. So for 22, it's giving you an equation. You'll have an equation on our final exam. It's not going to be this. Maybe it'll be this one. Who knows? Is heat absorbed or released? This tells you everything you need to know. Is heat absorbed or released? Which side has greater potential energy, reactants or products? Remember this. Let me erase all this stuff. Well, I guess it's erased on yours, but let's erase all this stuff. Which side has greater potential energy? Boom, boom. But you got to know which graph are we talking about? Negative 92 kilojoules. Would that be exothermic? Would that be endothermic? All right, so you're going to need to answer these three questions for each one of these two equations. And if you don't understand, I should certainly be there by Monday. So feel free to come in at lunch on Monday or Tuesday, and hopefully we'll do well on the exam. All right, I'll see you next time.